A machine the size of a double-decker bus etched features onto silicon yesterday that are narrower than a strand of DNA. And that same day, two independent research teams concluded that the encryption protecting your bank account, your email, your cryptocurrency, all of it, could be cracked before the end of this decade. And in a hospital in Stockholm, a single injection into a deaf teenager's inner ear gave her hearing she'd never had. Three different stories, all from yesterday, each one redrawing a boundary that used to feel permanent. So let's start with the silicon. ASML, the Dutch company that makes the equipment that makes every advanced chip on Earth, demonstrated a new lithography system that patterns 8 nanometer features onto silicon wafers in a single step. Now, to give you a sense of scale, a human hair is about 80,000 nanometers. A DNA strand is about 2.5 nanometers. We're talking about etching structures only a few times wider than a strand of DNA, reliably at industrial scale. The result is a 2.9 times increase in transistor density per chip, nearly 3 times more computing power in the same physical space. And ASML has already shipped about 10 of these systems at roughly $400 million each to both Intel and SK Hynix. This isn't a lab curiosity. This is in production now. Why should you care about transistor density? Because everything running in the background of your life, every AI assistant, every search result, every route that your GPS calculates runs on chips. And the demand for more powerful chips is growing faster than the chips are actually improving. Training a single frontier AI model now requires clusters of tens of thousands of GPUs running for months. The intelligence era is hungry for silicon. ASML just demonstrated that the physical world is answering that hunger and tripling what each chip can do, which means either the same capability at a third of the energy or 3 times the capability at the same energy. That is not an incremental upgrade. That trade-off reshapes what is buildable. ASML's head of research metrology described the demands as monumental, and here's what sits underneath that word. The previous generation of these EUV machines used a 0.33 numerical aperture. So essentially, that's a measure of how much light the lens can gather. But this new system pushes to 0.55. Now that sounds like a really small number, but in optics, it is the difference between seeing a house from space and seeing a license plate. The engineering required to make that jump, mirrors polished to atomic smoothness, light sources generating extreme ultraviolet radiation from molten tin droplets. This is physics at its absolute edge. And the trajectory points somewhere even wilder. At these scales, quantum effects stop being a nuisance engineers have to work around and start becoming a design feature. Which brings me to the second story of today, because yesterday quantum computing stopped being a problem for the next decade and became a problem for this one. So 2 independent research teams, one a Caltech spinoff called Oratomic, and the other, a group at Google, published analyses, both concluding that current encryption could be cracked with as few as 10,000 qubits. The previous consensus was millions of qubits and a decade or more away. That consensus collapsed. Oratomic's co-founder, Doliv Blofstein, said something that stuck with me yesterday. He'd been giving talks for years, saying that you needed millions of qubits to threaten encryption. But then his own team's analysis came back, and the number was 10,000. Scott Aronson at UT Austin called these papers quantum computing bombshells. So let me translate this into your life. P256 elliptical curve cryptography, that's the specific system that these teams analyzed, is one of the standards protecting your online banking, your encrypted messages, HTTPS, the little lock icon that's up in your browser, cryptocurrency wallets, Cloudflare, which protects roughly a quarter of all internet traffic. A mathematician at Tsinghua University said that the findings have prompted conversations ranging from academics to bankers to people who care about cryptocurrency. So here's the thing. We already have post-quantum encryption standards. NIST finalized them back in 2024. The math exists, but what doesn't exist yet is the migration, the massive, grinding, boring infrastructure project of swapping out the encryption underneath every website, every banking system, every government database, every messaging app. That migration was supposed to happen over the next decade, comfortably in planned phases. But what these papers just did is compress the timeline so that comfortable is no longer an option. Organizations that were treating post-quantum cryptography as a line item in their 2030 planning documents now need it in their current budget cycle. And I want to name something that the Century Report has been tracking across domains here: fusion energy, RNA biology, chip design, drug discovery. The distance between theoretically possible and arriving soon keeps shrinking faster than the experts in each of these fields expect. On February 13th, one of our earliest editions, we documented the same compression in fusion timelines. On March 30th, it showed up in AI-generated drug pipelines being priced as production-grade pharmaceutical inputs. And now it's here in quantum computing. The researchers themselves are surprised by their own results. Now, that pattern, experts revising their timelines downward, is one of the most reliable signals of the generative era. But here's where this connects back to the ASML story in a way I find genuinely beautiful. The same quantum effects that threaten encryption are also the phenomena that chip designers are starting to encounter at 8 nanometer scales. The capability that cracks security is the same capability that simulates molecular interactions, discovers new materials, solves optimization problems classical computers choke on. So you can't separate the threat from the promise. They are the same physics. The question is whether the migration, the encryption infrastructure, the governance, the institutional response will move fast enough to stay ahead of the hardware. And fast enough is a question that just got redefined. Okay. So from the quantum to the deeply human, because what happened at Karolinska Institutet is one of those stories that changes how you think about what is permanent. 10 patients, all of them born deaf due to mutations in a single gene, OTOF. That gene is responsible for producing otoferlin, which is the protein that transmits sound signals from the inner ear into the brain. And without it, the machinery of the ear can be perfectly intact, but the signal never reaches the brain, so silence from birth. So the researchers delivered a working copy of the OTOF gene through a single injection into the cochlea, the spiral-shaped structure of the inner ear, one shot. And within a month, most patients showed measurable hearing improvement. And after 6 months, average hearing thresholds shifted from 106 decibels, profound deafness, to 52. That is the difference between hearing nothing and hearing a normal conversation. So a 7-year-old girl in the trial regained nearly full hearing. 4 months after treatment, she was holding everyday conversations with her mother. But think about that for a second. A child who had never heard her mother's voice, hearing it for the first time because of a single injection. Now, what makes this structurally different from previous gene therapy results is the age range. Earlier, smaller studies had only shown success in very young children, and there was a prevailing assumption that the therapeutic window closed really early. But this trial included teenagers. It included even a 24-year-old adult, and it worked across the entire range. So that's not just good news for 10 people in this study. It means the window of who can be helped is far wider than anyone had assumed. Now, the safety profile was clean. The most common side effect was a temporary dip in a type of white blood cell. No serious adverse reactions over 6 to 12 months of follow-up so far. And here's where the trajectory really matters most. Lead researcher Mao Li Duan said that OTOF is just the beginning. The team is already extending this same approach, the same viral vector and the same delivery method, to GJB2 and TMC1, which are genes responsible for far more common forms of genetic deafness. OTOF affects a relatively small population. GJB2 is the most common cause of hereditary hearing loss worldwide. And each successful trial de-risks the platform for the next gene. The delivery system, the engineered virus, and the injection route, the dosing protocol becomes reusable infrastructure. What was proven in 10 patients becomes applicable to millions. This mirrors something we've tracked relentlessly. On March 30th, Eli Lilly priced an AI-discovered drug pipeline as a production-grade pharmaceutical asset. Just 2 days ago, the second oral GLP-1 pill reached the market and expanded the patient population rather than just serving existing patients. The pattern is the same each time. A medical intervention moves from theoretical to proven. The platform generalizes, and the population it can reach expands by orders of magnitude. Genetic deafness is becoming a condition with a treatment and not a permanent thing. And the speed of that shift, one injection, measurable results in a month, compresses the emotional timeline too. So the difference between diagnosis and hope just got very, very, very short. All right, let's shift away again. Google released Gemma 4 yesterday under Apache 2.0, and I want to explain why that license matters more probably than even the model. Previous Gemma releases were open weight, meaning that you could see the model's parameters, you could run it yourself, you could even modify it, but you were still operating under Google's terms, Google's rules about what you could and couldn't do with it. Apache 2.0 changes that completely. It's one of the most established open source licenses in the world. Decades of legal precedent. Every corporate legal department knows exactly what it means. And what it means is take it, change it, sell it, deploy it. No permission needed, just give attribution. The model family spans 4 sizes. The 2 big ones, a 26 billion parameter mixture of experts and a 31 billion dense model run on a single GPU. The 2 small ones are designed for phones, optimized with Qualcomm and MediaTek for mobile deployment. Google claims the 31 billion model will debut at number 3 on the Arena leaderboard among all the open models. Now, this arrives the same day that Cursor launched Cursor 3, which is an entirely rethought coding interface where developers don't really write code. They manage teams of autonomous AI agents, and they write the code. So multiple agents working simultaneously across multiple code repositories. And Simon Willison, who's the co-creator of Django and one of the most respected voices in software engineering, went on Lenny's podcast and described that this is a new way of what working actually feels like. Faster, yes, more productive, absolutely, and mentally exhausting by midday, he said. The cognitive load of managing parallel autonomous agents, reviewing their work, catching their mistakes, keeping context across multiple simultaneous tasks, it exceeds what human attention was really built for. You're not coding anymore. You're air traffic controlling a whole fleet of AI coders. And that's a fundamentally different kind of tired. Put these 3 things together. The models powering these agents are becoming freely available infrastructure more and more. No licensing friction, no permission gates. The interfaces for directing those agents are becoming management dashboards rather than code editors. And the humans doing the managing are hitting cognitive walls that nobody planned for. This is what a phase transition looks like from the inside. This is not a neat story about technology getting better. It's messy, it's exhilarating, exhausting, but it's reality. And it's where the tools, the interfaces, and the human capacity to use them are all evolving at different speeds. So we'll cover a few of today's other releases as well. Microsoft released 3 new foundation models through its Foundry platform. MAI Transcribe 1 handles speech in 25 languages at 2.5 times the speed of their existing service. MAI Voice 1 generates up to 60 seconds of audio in about a second with custom voice support. And MAI Image 2 is an updated image generator focused on photorealism, all available now. Omnivoice, which is a collaboration between AI4 Bharat and the Omnivoice team, open sourced a text-to-speech model supporting over 600 languages and dialects with voice cloning from just a few seconds of reference audio. 600 languages, and that's open source. And AMD released Lemonade, an open source local inference server that works with both GPU and NPU hardware, exposing an OpenAI compatible API. So if you've been wanting to run models locally without the setup headache, it's really worth a look. So big day for open source. Here's what I want you to hold today. Yesterday, we drew 3 boundaries simultaneously. The physical boundary of how small we can build, pushed to near atomic precision. The temporal boundary of how long our encryption stays safe, compressed by years in a single pair of papers. And the biological boundary of what deafness means, transformed from it to treatable with a single injection. Each of those boundaries felt fixed even a week ago. None of them are fixed now. So very soon, watch for the first major bank to publicly announce an accelerated post-quantum migration timeline. Watch for the Karolinska team's GJB2 trial enrollment, because that's when this gene therapy platform reaches the most common form of hereditary deafness worldwide. And watch for what happens when Apache 2 models start powering the autonomous coding agents that are already reshaping how software gets built. Tools are free. The interfaces are shifting. The question now is whether we can redesign work itself as fast as we're redesigning everything that the work depends on. We'll see you tomorrow.